Yeah. So unfortunately, last time almost half of the lecture was muted. So whoever was here in person, they could hear it. And the people who were online missed it. So I'm going to repeat it, but I guess there's no harm done in repeating since we're meeting after such a long time. So just to remind you, uh, we are pretty much focused on Tomita's main theorem and the modular automorphism groups and the KMS condition and such things. Although we have not given a rigorous proof, we have tried to make sense of why such a proof or why such a strategy would have to be used. So before I got muted, this is the definition I had given, the centralizer of a state. So if you have a state omega, so let's say you have a C star algebra A, and you have a state omega on A, then centralizer of omega so is defined as all those h's such that omega AH is equal to omega HA for all AN, or in other words, omega of the commutator of A and H is equal to 0. All right. So if we have, let's say, a faithful normal state on a one-Neumann algebra,
Is there an issue? Video is not coming.
hello, can you hear me?
Yes.
Okay, so I'll resume. There was again a power cut. So now, this time I made sure I'm not muted. All right, so here, if you have in our setting, oh, I see. So until the power is back, the projector is not going to work. Why are they not fixing this UPS system? So I'm really sorry. Actually, the projector here is off, so the people here cannot really see what's going on. So maybe we'll wait for 4 or 5 more minutes. Do you have mobile devices with you where you can watch this? So try that for the moment, and when the power is back, we will put it. Or maybe some of you can get together and maybe watch it together. Like for example, Indrajit, you have device, right? Maybe you and so someone you can just pair up and watch it. That is much easier. Okay, so let's continue. So in our context, the thing we were interested in, omega is a faithful normal state. on a one-dimensional algebra R, which is so because it's a faithful normal state, we saw that if you look at the GNS representation, what you'll get is the corresponding cyclic vector will also be a separable vector. So in that case, the theorem that we had proved showed that R of omega, so the one-dimensional algebra is R of omega, the centralizer of omega is the set of fixed points of the modular automorphism group. The modular automorphism group. Okay. After that, what we okay, yeah, I guess we had a quick corollary also. So let me just mention that. So if omega is a state of a one-dimensional algebra R, and alpha T is a one-parameter group of star automorphisms, and alpha T is a one-parameter group of automorphisms. And satisfying the modular condition relative to R. So this one-parameter family satisfies the modular condition relative to R. Then if each alpha T is the identity automorphism, so if the modular automorphism group is in fact yeah, this was almost a borderline trivial corollary, automorphism I of R, then omega is a tracial state. Conversely, if you have a faithful tracial state, so conversely, if omega is a faithful tracial state, then the modular automorphism group is trivial. So yeah, so the context was that when we're talking even in the matrix example, if you had started with a tracial state, we'll not get anything interesting. So only if you have a non-tracial state, the modular automorphism group actually gives you a lot more information. And then our key goal in the second half of the previous lecture, which we are going to pretty much repeat, the key goal was to show some sort of uniqueness. How closely is the modular automorphism group associated with this faithful normal state omega? And as usual, so we just keep in mind that once you have omega, then you look at the genus representation, you have this x omega. And then here you have this map delta, only after you have represented your one-dimensional algebra R. So you have pi omega of R here. Then you have a corresponding delta acting on, so let's say pi omega of R x omega. So this is densely defined in general. And delta was defined as a map. So pi omega of A x omega is equal to pi omega of A star. Sorry, no, this was not delta, my bad. This was my map S. So essentially, this was the cyclic vector U, cyclic and separating vector U that we had denoted. S of AU is equal to A star of U. So in that sense, so you have this sort of isomorphism. So composing all of that, so you have the one parameter group of automorphisms. The modular automorphism groups looks like this. So pi omega of A goes to delta IT, pi omega of A, delta to the minus IT. So you can just pull it back to R. So alpha of T of A is exactly delta to the IT, pi omega of A, delta to the minus IT. So now this is again an element of pi omega R. So then you take a pi omega inverse. So although we had done it in a represented case, but you can talk it in an abstract sense, and then you have this one parameter automorphism group. So the theorem that we want to prove is the following. omega is a faithful normal state. On R, then there is a unique one parameter automorphism group. There is a unique one parameter automorphism group alpha T that satisfies the modular condition relative to omega. So that satisfies the modular condition relative to omega. So since I guess Pankaj has just started attending this lecture, so let me just remind you what is that modular condition. It just says if you look at this omega of alpha TAB and omega of B alpha TA, if omega was a tracial state, then these two will be equal. Like omega of AB will be equal to omega of B. But in general, you may not have an equal, but you will have a portal. So if you think of this as a function of T, so omega alpha T A times B, let's say A and B are some chosen, some fixed elements of R, then you have a function here. And omega B alpha T A, let's say you represent it as a function here, then the modular, like we say that this alpha T satisfies the modular condition relative to omega. If for any choice of A and B, if you're looking at these two functions, there is an analytic continuation between these two. So this typically you will call something like f of t plus I. This is f of t. F is continuous and bounded on this strip. On the strip Z, where imaginary part of Z is between 0 and 1. Okay, so the assertion is that this modular condition is so strong that it intimately ties omega and this one parameter automorphism group. So the only thing that can satisfy is that modular condition, is the modular automorphism group. And in order to show that, the Fourier transform makes an appearance. So that's why we had taken a step back. It looks a bit surprising, like at least in first glance, why someone would think of the Fourier transform. But the mantra that we should keep in mind is anytime you have a one parameter group, there is a Fourier transform lurking there. Like so for that, let's take a sorry, you have a question?
Analyticity in the interior of the strip, right?
Hello, yes.
Analyticity in the interior of the strip, right?
I think my volume is a bit low. Can you, sorry, can you ask again?
The analyticity of this function in the interior of the strip.
Yes, yes. So I said there is an analytic continuation. Yeah. So F is continuous and bounded on this and analytic in the interior. Exactly. So analytic in the interior of this strip. Yeah. So the point was you have these two functions continuous and bounded on the boundary, and you have an analytic continuation. Then that's how you are kind of transforming from here to here. And we had also very explicitly computed how it is related to the KMS condition. So where you had something like omega AB is equal to omega B sigma IA. So these are not that different, these two conditions. Okay. So in order to show that, we took a step back. We need Stone's theorem, which essentially describes all the one parameter like unitary representations of R. So it relates it to certain self-adjoint unbounded operators. So yeah, we have done a quick review. The review of Stone's theorem, because we'll be using this fact to justify why we should expect this sort of uniqueness. So we'll have to reformulate the this modular condition, which will make it clear why we should expect some sort of uniqueness. All right. So Stone's theorem is essentially, it looks like this. So you have a strongly continuous one parameter representation of R. So strongly continuous representations of R on a Hilbert space H are in one-to-one correspondence with self-adjoint operators on H, possibly unbounded. So when I say self-adjoint, so till now we have not seen really encountered unbounded operators. So the part is that after we finish this justification of Tomita's theorem and the surrounding ideas and this uniqueness theorem that I just mentioned, then we'll go back and try to do all of that we have been talking in the first 5 lectures or so in a very, very rigorous manner. So far, it was just giving you a flavor of the ideas involved. Okay, so Stone's theorem essentially says that if I have a strongly continuous unitary representation, I should say, strongly continuous unitary representation. So more concretely, you have this map T to UT. So T is in R, and these
This
are
is
unitary.
positive self-adjoint, right?
So do you really need positive? You don't need positive, right? Because anyway, anytime you have so if you want some sort of uniqueness, maybe you need positivity, but otherwise I can always shift it by minus 2 pi, right? It won't change a thing. So if I look at 2 pi, so this is always going to be equal to, sorry, my bad. You cannot do this, but so positive is not really necessary. Like if I give you any self-adjoint, I can always exponentiate it, right? I can always look at this. So this is already giving you a unitary group.
Yeah.
Yeah. So you do have a strongly continuous unitary group, even if. So what exactly? So are you saying that any unitary representation is the exponentiation of a positive, like the derivative at 0 is, because even in the case of one dimensions, I can give a counterexample, I believe. So here, if you, yeah, you just invert the direction, right? E to the minus. So you look at e to the minus ith. You just so you just take a reflection of this representation. Then the h that you have is the minus h of the original representation. So if you started with a positive thing, now you have a negative thing. So yeah, so you don't really have a correspondence where you necessarily need positive. I don't know if you can always find a positive. I'll have to think about that. Probably not. If you look at a one-dimensional representation, then you're looking at e to the itr, right? But then I can always invert that. Then I have e to the minus itr, and there's no way you can find a positive thing which matches up with this. Okay. So yeah, so you don't really need positivity here.
Okay.
So yeah, Stone's theorem essentially says that strongly continuous unitary representation of R on a Hilbert space H is in, yeah, since I'm not justifying, like the recipe that we'll use to find this self-adjoint operator, or at least identify, although again, because it involves unbounded operator theory, we'll not do a rigorous proof. So the recipe that we'll use will kind of extract out an H, but uniqueness, so we'll have to see as we go through the like rough idea of the proof, we'll see whether uniqueness comes out of it. But yeah, the key idea here I want to stress is that even if H is finite dimensional, this is a non-trivial theorem. So Stone's theorem is non-trivial even for matrices, I would say. So for unitary, like finite dimensional unitary representations of R is non-trivial for H equals, let's say, C to the N. So in a way, whatever we have done so far, at least in the matrix case, it was completely rigorous, right? What I'm saying is, even at this point, even in the matrix case, we are not going to be rigorous, because Stone's theorem essentially says that, and by the way, in the finite dimensional case, strongly continuous just means continuous. You have all topologies, all like locally convex topologies will match up. So I don't have to say strongly continuous. I can also say non-continuous. But any such unitary representation, like finding this H is, again, this H will be this self-adjoint operator, again, will be a bounded operator in that case always. But proving that is the case, that you have such an H is not so easy. Okay. Yeah. So since Stone's theorem is about representations of R, so let's take a step back and try to understand. So R, you have a group G. So this is, let's say, a finite group. So we have been always drawing this sort of analogy. And now this is a non-compact Lie group, you could say, non-compact semi-simple Lie group. Okay, so the general strategy, if you want to study representation theory of a finite group, is look at regular representation, left regular representation, because it contains all the irreducible representations. And then you realize, once you figure out character theory and all, then the number of irreducible representations is equal to number of conjugacy classes and so on. But in any case, CG is the thing that we want to look at. And typically, the vector space in the regular representation is also CG. And the way you multiply, you act CG on this. So this algebra, this group algebra, is by left multiplication. But at the level of, but multiplication on CG is actually convolution, right? On CG is a convolution. Now, if I want to use this analogy, I want to build some sort of left regular representation. I need some version of CR. I'll put a question mark. Then I want some version of CR here. Then I want to do some sort of multiplication at this level. And again, in this case, it will turn out to be a convolution. But here, since it's not a finite group, we need to, and G, we have an interpretation in terms of functions from G to complex numbers, right? C of G. And since this is finite, then this is a finite dimensional vector space. So what we care about are functions from R to C. But is it any class of functions? Typically, we want a nice class of functions, where you have control, where maybe you can do some integration, where you can count. Here, everything is finite, so counting is easy. Here, if I'm looking at arbitrary functions from R to C, I don't really know what to make head or tail of it. So typically what you do is, as a proxy for this complex group algebra, use L1R. And here, what I'm going to suggest is to use L2R. Because we want a Hilbert space. I can always put an L1R here also. Then convolution of two L1 functions by Young's inequality is again L1. So if you have two L1 functions, then you have in fact, if I convolve an L1 function with an LP function, you have F convolve G is going to be LP, and the LP norm will be less than L1 norm of F and times LP norm of G. So in that case, I could have always replaced this, but I want a Hilbert space. So that's why I'm looking at L2R. And like I said, for P equals 2, Young's inequality also tells me that if I have a function F in L1R, I can define this LF from L2R to L2R, which is given by LF acting on G is nothing but F convolution with G. Okay, but so here there is so if you want to do everything carefully, just look at chapter 3 of Cadiz and Ringrose. But there is a difference between this algebra. Now L1R with convolution is a Banach algebra, even in fact a Banach star algebra, you can say. And it doesn't have a unit. You can in fact show that. So without unit, you can always append a unit, but it doesn't naturally come with unit. It comes with approximate units. Things like mollifiers, things like that go to a delta function. Those are like that family is like an approximate unit. Now this, I'll have to use some other notation now. So L1R, just to repeat myself, acts on L2R as a convolution algebra. And here, I can build another C-star algebra. So it acts on L2. Now you're thinking of each element as LF. Now I look at span of LF, span of LF closure. So this is a C-star algebra. So I'm just taking norm closure of this in B of L2 of R. And it may not, again, in fact, it will not have a unit. You can show that LF minus identity is always has norm bigger than half. So in fact, even the C-star algebra, so look, these are somewhat different. Like this is a Banach algebra. Here we're just not really talking about any representation of L1R. Here we're very specifically talking about a certain representation. So there is a certain difference between this. So when you're trying to build intuition from here to here, for example, here you have something known as a Fourier transform, right? Anytime you have an L1R, it is in fact a homomorphism to C naught R. So some sort of homomorphism. So something similar will also happen here, but it will be a little bit convoluted proof because these two algebras are not the same. The translation will take some effort. So I just want you to leave with that point. But yeah, so this is not unital, but you can always unitize it. And the unitization I will denote by, so this is norm closure of L1R. So it's this exactly is norm closure of L1R acting on L2R. And then unitization of this. Just write it this way. This I'll denote by naught. So this is like a maximal ideal. So just to repeat myself, first of all, you have L1R. It is under convolution with itself. You have it's a Banach algebra without unit. But if I'm representing L1R on L2R by convolving with L2 functions, so if that is the thing I'm using, then each element of L1R, I'm associating a function, an operator LF acting on L2R, and I'm taking span closure that does not contain identity. That needs a proof, but I'm skipping that proof. Then if I add the unit, then I get this A naught R. Okay. So one thing to note is L1R is a commutative Banach algebra. So R is a commutative group. This is a commutative Banach algebra and so on. The group ring of a commutative group is again going to be a commutative algebra. Okay. So now if I'm trying to study representations of G, so what happens is unitary representations of G are in one-to-one correspondence with unitary representations of C of G, like modules, CG modules. We have seen this. So similarly, we want to look at somewhat like this, either you can say L1R modules, but the more accurate thing would be to say that you want to look at this A1R modules. Okay. So anyway, you have this sort of functional A naught of R to C given by rho infinity of identity is equal to 1 and rho infinity of A1 of R is equal to 0. So effectively on A1R, it is a 0 functional. All you have done is defined it to be 1 on identity. And if you have 2 times identity, whatever, lambda times identity, you define rho infinity. So rho infinity is a multiplicative functional on A naught R, which vanishes. So multiplicative functionals, you can think, I think the better way, instead of say multiplicative functional, is like you think of it as a homomorphism. So homomorphism onto something a very trivial sort of Banach space, which is complex numbers. So you're looking at, let's say, like one-dimensional representations. Since you have a abelian group, let's say finite abelian group, the irreducible representations are one-dimensional. So you do care about those things. So you can think of this as motivating why you care about multiplicative functionals on this commutative Banach algebra. And of course, we know all that Gelfand-Neumark theorem and Gelfand transforms and all those. So this vanishes on A1R. Yeah, but by the way, all those Gelfand theorems would have been actually more directly applicable to L1R star. Like here, one has to be a little bit more careful. Again, like I said, it needs a bit more proving, but you can already guess what sort of strategy to take. Okay, now let's say M naught R, a lot of associations are going to happen, is a set of all non-zero multiplicative functionals. Functionals on A naught R. For example, this M naught R will not contain rho infinity. So rho infinity does not belong to this M naught R. So these are all non-zero multiplicative functionals on A naught R. So it's A naught R is the one that is, did I say A naught R? Yeah, right. Yeah, so these are like the multiplicative functionals on A1R. Yeah, anytime you have A naught, non-zero, you just restrict, it will still be non-zero here. Yeah, maybe I should say it is on A1R. The question is, the definition of M naught R doesn't seem to be very clear. So let me repeat. So it's non-zero multiplicative functionals on, yeah, so maybe I should add which do not vanish on A1 of R. Okay, so you have rho infinity. So here's a theorem from L1R to C is multiplicative. That means you have a, so this you're thinking of as a Banach algebra under convolution, and you have a one-dimensional representation of that. So that's what it means to be multiplicative, if and only if there exists a real number R such that rho of F is equal to F hat of R. Okay, so let me quickly define what is f hat of r. So the Fourier transform, so you have an L1 function, the Fourier transform at t will be integral e to the, so if I don't know if I want to be very, so Cadison prefers e to the minus itx, but Rudin prefers e to the minus 2 pi I, which I am much more used to, like even Stein prefers that. But to just be consistent, I'll use e to the minus itx over, so f hat of t is this. So if f is an L1 function, of course, this product is also an L1 function. So this makes sense for all t. And for convolutions, just by using Fubini, you can see that this is in fact multiplicative. So if I have f convolve j evaluated at t, then you have e to the minus itx of f convolution with g, x dx. Then I'm going to write out the definition of convolution. So then I'll have x minus y, gy dy dx. Then I move things around, move dx here, dy there, using Fubini's theorem. Then what do I get? And I split this part also. Now I'll have this, I'm writing as e to the minus it x minus y times e to the minus ity, which I'm going to, so I have not used Fubini yet. So here I'm going to use Fubini. So integral r e to the minus ity gy integral f of x minus y e to the minus it x minus y dx dy. Now for every single value of y, it doesn't really matter. You're just you're just finding the Fourier transform of f at t. So I can in fact separate this out. So at the end result, you get f hat times g hat t. So in fact, the Fourier transform evaluated, so you choose your real number t. Then if you the mapping, if you define it this way, it's going to be multiplicative. So what I'm saying is that the converse is also true. Anytime you have a multiplicative function, then it has to be of this form. Again, that needs a proof. Typically, what will happen is that so you have rho of fr so f convolution gr will be the same as this. So this is fr times rho g. This is rho f times rho gr. Yeah. So, I mean, the general idea of the proof would be the following. So this is something you can prove if you translate this function. Oh, by the way, I never defined gr. So gr is nothing but gr of x is g of x plus r. It's just translation by r. So if you convolve f with the translation of g, the same translation you can use on r. Again, you just look at the definition of the integral. This will be clear. Now, because rho is a multiplicative functional, you'll have rho of f times rho of gr is rho of fr times rho of g. Now, what this means is this thing. Rho of fr divided by rho of f is equal to c for all f. So for any given r, you'll have rho of fr divided by rho of f is equal to c. And I guess you have to assume non-zero, I believe. So non-zero, because otherwise you cannot. You have to figure out some f where this is non-zero, and then you have rho of fr is equal to, then how do you figure out the t or r rather? Yeah, so then what you'll have to prove is like rho of fr plus s is equal to rho of fr times rho of fs. You have to prove some sort of multiplicativity, and eventually you know that all multiplicative maps from, like all continuous multiplicative maps from r to c are given by r going to e to the itr for a fixed t. So you'll have to use that fact here. So roughly this is how the proof goes, but let's assume this theorem for now, that every non-zero multiplicative functional is just given by evaluate f hat. Actually, I could have also included zero by saying that f hat of infinity is equal to zero. So why is that? You have something known as Riemann-Lebesgue lemma, which says that if I start with an L1 function, so let me state that here. So Riemann-Lebesgue lemma, this is one of the first theorems you see when you start talking about Fourier transforms. is that if f belongs to L1 of R, then f hat belongs to C naught of R, meaning it is a continuous function vanishing at infinity. Function vanishing at infinity. Okay, in any case, so I could have said that if I had allowed R equals infinity, this would have been that all multiplicative functionals are given like this. All right, so now we saw that anytime we're talking about representations, very, very naturally, a Fourier transform has to show up. And here's yet another theorem which will not be proved, but it's transfer of a theorem from L1 to A naught. I said there is a subtlety there, right? L1, it is like the Fourier transform we are more directly defining. So now I'm going to say a similar result for A naught. So there is a homeomorphism. Lambda from M naught of R to R. So remember, what was this? This was set of all non-zero multiplicative linear functionals on A naught R, not on L1, but rather on A naught, which was acting on a Hilbert space and so on. So you have this such that rho naught of LF is equal to F hat of lambda rho naught for all F in L1 of R and rho naught multiplicative, non-zero multiplicative functionals, or rather I should say I had a definition, right? Rho naught belongs to M naught R. So let's stare at it for a bit. So what I'm saying is, now if I look at the set of all multiplicative functionals in M naught R, those functionals which are not vanishing on A naught of R, so that was the one we had constructed from L1 R acting on L2 of R, then such functionals are just given by the ones that we had from L1 R. So F hat of R, so this was F hat of R, so this is lambda of rho naught. So is this clear? Like what's going on? Okay. Okay, so in a sense, we are saying that it is parameterized. The set of all linear functionals are parameterized by M naught R. And in fact, if we had added that trivial functional, we would have gotten some sort of compactification. So if you look at, actually not really a compactification, because that is isolated, right? That is an isolated point. So yeah, so maybe it's just R union infinity, like an isolated point. I'll have to. Yeah, I'm just thinking maybe because of Riemann-Lebesgue, you will have one-point compactification because the functions will match up on both sides. But yeah, maybe it is the one-point compactification. No, the reason I'm a bit worried is because if I'm looking at all multiplicative functionals, then rho infinity is actually an isolated point, right? Is it not true that rho infinity is minus of rho naught, like is bounded below by some epsilon? I think so. So if it were approachable using these sort of states, then you would say that, okay, there is a one-point compactification happening here. But I believe that rho infinity is actually something isolated.
Which norm you use?
Like functional, like norms and functions.
The area is I'm talking about base term.
Yeah, right.
Not in that case.
So rho infinity is not isolated in weak star sense. So not isolated in the weak star. Weak star topology. Yeah, because at some point I think we'll be using representations of abelian sister algebras. So maybe we will lead this to be compactified. So representations of S1. Okay. All right. So if we accept this, now we are ready to kind of give a heuristic for Stone's theorem. I'll restate again. So if H is a possibly unbounded self-adjoint operator on the Hilbert space H, then P going to e to the ith is a one parameter unitary group. So one parameter, we suppress that it is strongly continuous, but whenever someone says one parameter unitary group, it typically means strongly continuous. Strongly continuous. This is somewhat easier to check once you understand spectral theory of H. So what you need to do is, like, let's say H has an unbounded spectral decomposition, so minus infinity to infinity. So if H were a bounded self-adjoint operator, this instead of infinity, you could have replaced with the norm H. So you have an unbounded spectral decomposition. And if you look at the spectral projection of e to the minus n and n, then any vector, if you look at in the range of e to the minus n, so you look at Hn. These, by the way, all commute. So these projections all commute with H. Of course, whether H generates an algebra or not, that has to be made sense. But yeah, it does generate something known as a Murray von Neumann algebra. These are all self-adjoint operators, unbounded self-adjoint operators. So in any case, if you have such an X, you can show that e to the ithx goes to X as t goes to 0. So that is what you would mean by strongly continuous. So in fact, all you need to do is prove it at 0. Then it will be strongly continuous at any other point. So e to the ithx will go to X as t goes to 0. Because this will literally behave like this operator Hn. In fact, e to the ithx is exactly equal to e to the ithnx. And for bounded operators, we know that this is true. So the first part is pretty straightforward once you understand spectral theorem for unbounded self-adjoint operators. But the converse is the non-trivial part. So converse is very much looking like this. This, I said, is a non-trivial theorem, right? One way is clear, is that if you look at the Fourier transform, you evaluate at a point, it is giving you a representation. But then the converse is the harder part here. What I'm saying is any one-dimensional representation looks like this. So Stone's theorem is you can say, a non-commutative version or a higher dimensional version of this. So one direction is easy. Now you're saying conversely, if this is a one-parameter unitary group, on H. So another way of saying it is strongly continuous representation of the real numbers. Then there is H. Self-adjoint, possibly unbounded. Such that u of t, by the way, even if H is unbounded, e to the ith is always going to be bounded because of function calculus. Even if you take a really big number, when you exponentiate, the modulus is always going to be 1. So this is always going to be a unitary. And there is a little bit more to be said. And domain of H is equal to all the set of all vectors in the Hilbert space, such that limit of t going to 0, utx minus x divided by t exists. So this, if you remember, I mentioned that even if H is finite dimensional, this is a non-trivial theorem. So it is not at all clear that this utx kind of is a differential. It is continuous, will be clear that if I remove this bottom t, it is clear that as t goes to 0, utx will go to x. In the matrix case, it is very easy to see. I mean, just from the non-continuity. But what I'm saying here is utx minus x divided by t, this limit exists for a dense set of vectors. In fact, in the matrix field, it will say it exists for all vectors. So maybe you can play around and think about it, but it's not very clear that if you have a one-parameter group, that for all vectors x, this limit exists. But it will be a consequence of the study of the representation theory of L1R that we have seen. Okay, and so there's still one more part. And for f in L1 of R, you have f hat of H is equal to integral f of t e to the ith dt. So it looks like Fourier transform. In fact, a version of the Fourier transform. So effectively, what does the left-hand side mean? F hat is a continuous function vanishing at infinity. So using continuous function calculus, I can make sense of what F hat H is. So this is some self-adjoint operator on the left. Okay, it doesn't have to be self-adjoint, but some normal operator at least, F hat of H. And on the right-hand side, what I'm saying is F of T, if you multiply with this unitary, this by the way is UT. So I can write it in another word, in other words as F of UT dt. Because this is, yeah, by our choice of H, if such H exists, it's integral FT UT dt. Okay. This kind of gives a hint as to how to proceed with the proof. Again, we will not be giving an exact proof, but we'll reduce it to the previous theorems that we have seen. So phi of LF, we are going to define as integral F of T, U of T. So anyway, UT is bounded, F of T is L1. So if I take a norm here, this is actually going to be bounded by the L1 norm of F. So if I take norm of this thing, so norm of integral R ft ut dt is less than equal to integral mod ft dt. So which is less than equal to L1 norm of F. So, I mean, you may ask in what sense? Really, what I should have written is I will define phi LF in this manner, x dot y. Then I can appeal to my function theory, f of t ut x uy. Now this is a function of t, which is bounded. So then I can say I have this conjugate bilinear functional, blah blah blah, and and it will correspond to some operators. Now the map x y going to this thing is a bounded conjugate bilinear functional. So there must exist some operator which I'm going to designate as phi LF. So that would be the rigorous way of saying it, but roughly we can make sense of what this means, this expression means. So what's the property of this? This is actually homomorphism. Because UT is a strongly continuous parameter group, because if I multiply two such things, LF and LG, this by definition is nothing but L of F convol G, which will turn out to be integral F convol G of T ut dt, and you do the same proof as before. To conclude, this is phi LF. So you use Fubini's theorem to conclude phi of LF times LG is equal to this. So phi is a representation, and it is also norm-boundedness of this representation will be there. So it's a continuous representation, norm-continuous representation of L1R. Sorry, on H. So what that will give us is that it will extend to a representation of A1 of R. And then you just extend by identity, you just send it wherever you like. So, yeah, so then, I mean, one step here that is remaining. So you have to figure out what this so based on you figured out this representation phi. Yeah, right. So another intuition that you should always keep in mind is what Stone's theorem is saying. I've mentioned this before also. If I just formally look at e to the dd, excuse me. Excuse me. So e to the t ddx, this, if you look at like this, t squared over 2 factorial d squared dx squared, and if I apply this on a function f, now think of this f as being a vector, right? It's a vector in a Hilbert space, you know, a dense subset of the Hilbert space, so like smooth functions and so on. This is generating a translation by t, right? This is by Taylor series. This is the Maclaurin theorem or whatever, Taylor's theorem, is saying that e to the t d dx of f is equal to tau t of f. So this is the generator of translations. Okay, so in this case, that is what ut is also going to do. So u of r of phi L of f of x, instead of ut, let me just write this. So it is going to translate this function. So really, phi, whenever I have written phi of LF, I'm writing it as a proxy for f, right? As representation of f. via many different F first I associated with LF, then I use this map P. Now this you can show is exactly the same as P of LFT of X. So this UT is behaving like this generator of translation. So this, the infinitesimal. So very rigorously, we have been able to identify it as an infinitesimal generator of translation. Now what you have to do is use this association that we have. We have this map P hat of F hat, which is equal to P of LF. And how do we define this phi hat? It's a very forced sort of definition. Like, I mean, this is the expression which defines this. So this equality, either you can say it's an equality, or I can say this is the definition of phi hat. And it's a consistent definition that needs a proof. And that you can see by looking at these maps. So you had this homeomorphism. Not of R. So phi hat, F hat. So LF. So we had this theorem, right? Which so rho naught of LF is equal to F hat lambda rho naught. So I want to define what is phi hat of F hat. So I just need to define what it is on R. So phi hat of F hat. Yeah, right. I mean, so either you can trace the relation between LF and F hat, which we did it via some sort of the Fourier transform. Like it was a homomorphism from this convolution algebra to this. So you do use that homeomorphism, and then you compose that, and again to look at the inverse transform in some sense. So if you use this is actually a consistent definition, right? F hat, phi hat, if I define it in this manner, it makes perfect sense, right? Because if I have two L1 functions, F and G, then F hat, phi hat, G hat, by this definition is going to be a multiplicative functional like this. And not functional, but rather representation. Okay. So the phi hat is a representation of C naught of R, you could say. So as you vary all F over L1 of R, I'm not saying that the image of L1 R under the Fourier transform is C naught R. That is not true. In fact, if you decay slower than a logarithm, then you cannot be like, even if you're vanishing at infinity, you cannot be Fourier transform of an L1 function. But what we're saying is once we get to this L2 sort of description, that holds true. That is in fact a homeomorphism. So phi hat is a representation of C naught R. In fact, it will extend to a representation of C of S1. So you'll get a map from CS1 because C naught of R, if I do a compactification, it will, C naught of R is like a maximal ideal in C of S1. And here we'll use this. So where do this, so until here, H has not made an appearance because we're trying to kind of roughly justify the converse. But once you have this, so any sort of homomorphism of C of S1, or did I say R? No, my bad. I mean B of H, because we're trying to represent on H, right? You remember? Phi hat of F hat is this operator Phi of LF, which is acting on H. Okay. So you have this sort of representation, and you can use Hahn-Hellinger or a basic spectral theorem for normal operators or whatnot. So what you'll get is this, by the way, is generated by Z, right? You look at the polynomial Z in S1, Z square, Z bar, all these inverses in S1. Then all you need to do is know where Z is mapping. Let's say Z is mapping to T, then you know any polynomial in Z is mapping to P of T, and so on. Now you look at, so now you have this normal operator T that has a spectral decomposition. So you have certain E lambdas. So E lambda is the spectral decomposition of T. So image of this Z. So this will come in handy now. Okay, so what you have is so phi of LF is equal to integral ft ut dt, which is equal to phi hat of f hat, which is integral f hat and then you have this spectral decomposition of this t. So e to the 2 pi I z dez, let's say, or e to the 2 pi I t det. So now you sort of absorb this and you get r. So the corresponding h is nothing but integral of t det. No, but then this turns out to be bounded. I think I missed out something here. So from this t, oh, I see. So maybe I should not really have talked about representing CS1 using these polynomials. So in fact, this C naught R, when you talk about representation of this, then I mean, each such representation, this again needs a proof, but the general idea is this: it needs a proof, but C naught of R, this representation gives rise to a resolution of the identity. Anytime you have an abelian subalgebra of B of H, it always gives rise to a resolution of the identity. So let me, so any, so let's say abelian von Neumann algebra corresponds to a resolution of the identity. So that is what you will be using here. E to the 2 pi I lambda t det integral over R. And this need not be bounded actually. Yeah. And then H will be defined as integral over R of t det. Then formally, if you do exponentiation of ith, then you should get by function calculus, it should be integral of e to the 2 pi it det. And yeah, so that's how you recover your h. Then you equate these two things. And I guess you'll have to use a certain theorem about, so here I would like to say ut is equal to 2 pi ih. Maybe you want to look at the inverse Fourier transform here. Use something like fg dx is integral f hat g inverse Fourier transform dx. This is true for any two L1 functions. Yeah, but I hope you roughly get the idea where the Fourier transform is making an appearance. That was my main point. So this is Stone's theorem, and we're going to use it to prove our main goal, which was the close association of the modular automorphism group with a faithful normal state that we chose. Okay. So coming back to the modular automorphism group, you have alpha of t. So this is some one parameter automorphism group satisfying the modular condition relative to omega. Okay. So now alpha t, so if I take this, so remember this u was that cyclic and separating vector. So you have alpha t a star a u dot u is nothing but norm of alpha t a u whole squared. Now this is by definition omega u of alpha t of a star a. But we knew that this, if alpha t is satisfying the modular condition, so you have omega u of alpha t must be the same as omega u of a star a. So just remember, it was just a purely complex analytic sort of proof, like sometimes using Schwarz reflection, sometimes using Liouville's theorem. It was purely complex analytic proof. So all you needed was the modular condition, that there was some analytic extension. So in fact, for if you satisfy the modular condition, you'll have this omega u alpha t a star a is this. But again, reinterpreting this, you end up with au norm whole square. So overall, what you have is norm, and this is true for any u in the von Neumann algebra. You have this. So now using this, we are going to define a unitary operator ut. So ut is defined as ut of a of u is equal to alpha t a u. This is the definition. So it's defined on a dense subset. Also, it's an isometry, so I can extend that definition. So I got this unitary operator. So ut is a unitary operator. Okay. Now ut plus s au is by definition alpha t plus s au. But this is nothing but by the fact that this is a one parameter automorphism group. By the way, here I don't have to assume that it is strongly continuous. The modular condition will give something like that, as we'll see. So here you have alpha TA, alpha SAU. So first of all, I'm thinking of this as just some element here. So UT of AU. So I'm thinking of this as my A. Yeah. So I have UT. Oh, sorry. Alpha T of X acting on US of AU. Now, whatever this is, oh, my bad. So effectively, I want to end up with this conclusion that UT composed USAU. So how do I do that? So UTAU is alpha TAU. So this is USAU. Right, yeah. UT of what am I writing? This is some bogus thing I have written here. Sorry, my bad. Yeah, so this is actually not alpha TA times alpha SA. This is just composition, right? Alpha T composed alpha SU. And now thinking of this as just some A. So it's pretty straightforward. So just think of this as some B or something like that. So alpha TB. So by definition, it is UT of B of U, which is alpha S of U. Then again, applying on this part, the same definition, you have UTSAU. And now since U is a cyclic vector, as you run around all the U, you have this. So you have shown that U of T plus S is equal to UT times US. Now only strong continuity I have to show to get some sort of infinitesimal generator. So strong continuity will follow from the following fact. So norm of ut minus a I yeah, by the way, you have ut a ut star is equal to alpha t of a. Yeah, so this is clear because anytime I have so ut of ab Yeah, can you hear me now?
Yes, sir.
Sorry. Okay. So but just by using the definition of UT on, you take two elements AB in the one-dimensional algebra R, you have UT ABU is equal to alpha T ABU. So this, again, by using the fact that it's a one parameter automorphism group, it's an automorphism for every T. So you have alpha T A times alpha T B. Now here I'm using the fact that UT of BU is alpha T BU. Now I'm fixing A and varying B. Then what I get is, since U is a cyclic vector, BU is a dense in age. So overall, I conclude UT of A is equal to alpha TA of UT. So another observation is that, so in fact, alpha T is unitarily implemented by a one parameter group. So it looks very familiar. It's a bunch of inner automorphisms. So represented using inner automorphisms. And we know that our modular automorphism group is also looks something like this. It does look like a bunch of inner automorphisms. You had a delta to the IT, a delta to the minus IT, right? So the modular automorphism group looks something like this. So our end goal will in fact be to prove that these two things are the same. Delta to the IT is equal to UT. Then what you'll get is that, okay, this whatever alpha T we started off with ends up being the modular automorphism group. So that's the strategy of the proof. But there's one last thing remaining, that we didn't show that it's strongly continuous in order to be able to use okay. So strong continuity again will follow from the modular condition. So you have UTAU BU is equal to B star alpha TAU dot U. So why is that? So B star UT, I guess UTU is equal to, yeah. So one thing to remember is UTU is equal to U, simply because here you think of as an identity, and alpha T of identity is identity. So that's why for all T, UT of U is U. So and in fact, UT star of U is also of this vector U is going to be U. It's very similar to the properties of delta that we had seen, that delta of U is equal to U. So UT also has the same property. And that's why here I can always replace this vector U by a UT star. So that's why I get the alpha TA, then I'm just moving B. I'm taking the adjoint, I'm moving the B here. So I have this equality. And this is nothing but omega U of B star alpha TA. Remember that this is a continuous function, right? It's a continuous function in T. So continuous in T. And that is following from the modular condition. So continuous because of the modular condition. And this is what we need to show that this one parameter group is actually strongly continuous. So what does that tell us? It tells us that when T is equal to 0, T goes to 0. So as T tends to 0, you have UTAU BU tends to AUBU. Simply because you do this computation, you hit here, then you know that omega U B star alpha T of A goes to omega U B star of A, then you do the computations back. So what you have is UTAU BU is this. So then I just need to note that UT minus identity AU norm squared, just expand things out. This is 2I minus, so I'm just looking at the adjoint and multiplying things out. So this AU, this tends to 0 because individually we saw that UTAU will go to AU, and U minus T AU will also go to AU, and then you have a 2I minus, minus this. So overall, this will go to 0. So what does that tell us? That if I fix this vector by choosing this operator A, if I fix this vector, UT minus I of X goes to 0. And this happens on a dense subset. And these are all bounded, right? UT, everything, all of these are bounded. So what this means is UT goes to I in SOT as T goes to 0. So this happens in the strong operator topology. So summarizing all of this, what we have is the main takeaway is that you have this UT star. So you're implementing this alpha T using these UTs as inner automorphism. And this UT is a strongly continuous one parameter unitary representation. One parameter unitary group. Okay. So based on our previous theorem, there is some H, right? Based on Stone's theorem, there is some self-adjoint operator H, so that UT is e to the ITH. Our goal will in fact be to show that delta is equal to X of H. Remember, if we show this is equal to this, we are pretty much done. If we show this is true for all T, we are pretty much done. If we can show even something stronger that UT is equal to this, then we are done. Or in fact, we can go even further and say we'll choose, if H is such an operator, then delta equals e to the H. That's what we'll prove. So that's where all this business of Fourier transform comes in. Okay. So here's a quick proof of the following fact. We'll have to define certain class, but these are all technical because we want to make sure that functions are integrable, their Fourier transform behave the right way. But you can try to think of them as certain technical condition. So let F be all G in CCR. So continuous functions with compact support. Doesn't necessarily mean uniformly on a uniform compact set, but any function has compact support here, such that the inverse complex Fourier transform is L1 on lines. So this is true for all S. So how do we define G inverse? So this is the inverse Fourier transform. Integral R e to the minus I lambda Z G of lambda d lambda. Note that first of all, this makes sense for every single Z, this makes sense because G lambda is a CC function. So it's L1 function in particular. And the only issue that could happen is from the imaginary part, because in the real part, we know this is L1. Imaginary part will just contribute some fixed quantity. So this is in fact bounded. So G inverse Fourier transform is bounded on every region where imaginary part is bounded. Region where imaginary part of Z is bounded. So if you want to think of it, if I have a strip like this, so now remember this inverse Fourier transform, I'm not just defining it on R, but rather I'm extending this definition to all of the complex plane. So typically you would have defined it for G hat of T, something like T is a real number. But here I'm saying that, so this by Riemann-Lebesgue lemma on the real line, of course, it is bounded, but not just that. In any neighbor, like big neighborhood, big strip, as long as it is bounded, this G hat is going to be a bounded function. Another fact to remember is that this is actually an analytic function is Z. So G inverse Fourier transform is analytic. Simply because you use your favorite dominated convergence theorem, whatever, you want to differentiate with respect to Z, whether I can interchange this integral and this derivative, I just need to use that. And then when I have this lambda coming out, lambda times G is again going to be an L1 function because G is a CC function. So if I multiply any other continuous function, it is going to end up as a CC function. So modulo those technical details, what we have is G hat is analytic. And for such functions, so I have this family F now. So I'm going to prove a small lemma now. So integral, I'll define L in a moment. Integral over L over R of this function where I think L, yeah, so where L belongs to this. So F, remember, is consisting of all those CC functions satisfying certain condition that its inverse Fourier transform is actually L1. So here what I'm saying is I'm choosing a function L, taking inverse Fourier transform of these sort of CC functions. So that means I'm taking a function L whose Fourier transform is a bounded continuous function. By the way, this is a theorem, a well-known theorem known as Paley-Wiener theorem. You may have seen that if you have a function with compact support, its Fourier transform is going to be an analytic function. So in this case, you'll see some sort of holomorphicity kind of spreading because of compact support. So these are the technical conditions that we need to be able to cleverly use Cauchy's integral formula. So where this holds, you have this equality. Integral LT is equal to this. And as you can guess, these terms look familiar to us. In the modular condition, we have these terms. So let's try to quickly give a proof. You just look at a strip. You look at a big enough like this. There is an R here and minus R here. Yeah. So on this strip, and note that L is analytic. Using Paley-Wiener theorem, like I said, because L hat is compactly supported, that means L itself is analytic, and F, let's say, is analytic, and in fact, analytic in the interior, continuous and bounded throughout, continuous and bounded. In fact, these are the conditions that we need, right, for the F that we had omega alpha T A B. So that's why. So these are the conditions I'm assuming. Then I'm claiming this equality will hold. Oh, by the way, I never specified what F was. I just assumed that you guessed F was our favorite thing, which was omega alpha T of A B here. Okay, so in this condition, I'm saying that these two are equal, and all you need to do is standard techniques. You integrate throughout. So integral is 0 because the product is also analytic. Then I'm dividing into, so 0 equals integral over gamma of Lz Fz dz. So then I have minus R to R Lt. By the way, this is imaginary part Z equals 0. This is imaginary part Z equals 1. So Lt Ft dt, and then you have minus because of the orientation. So minus of integral minus R to R Lt plus I Ft plus I dt. This R, by the way, is different from this R. So here, this is like a script R. This is the real numbers. This is some bound. Maybe unfortunate notation, but think of this as a bounded set. And then you have an epsilon term, epsilon of R. So essentially what we'll like to show is this epsilon term kind of goes to 0. As I send S off to infinity, integral on this part and this part goes up to 0, and then I'll use dominated convergence theorem, simply because you have L is in F hat, you have F is continuous and bounded. Yeah, so then you can use continuous. So why is this L1 function? Is this clear why it is L1? F is continuous and bounded. Yeah. It's not clear why the integral makes sense, right? I mean, if L were the CC function, then we'd be fine, but then I cannot use analyticity. So let's look back at this definition. So you have G. Oh, yeah, it is because of this condition. So anyway, we'll have to show that this is a non-empty condition. We'll have to exhibit that F is not a trivial thing. And we'll do that at the end. Yeah, because L belongs to F, this, you do have this condition. Like, by the way, an analytic function can be bounded on strips. Of course, Duval's theorem says that it cannot be bounded on all C. So this condition should not look very suspicious. And a quick example for that you can think is sin Z over Z. On any strip, it will be bounded. It is in fact analytic because there's a removable singularity at 0. Or you can take something like, okay, I was thinking e to the minus x squared, but that is only for the real line. But yeah, this is a good enough example. So you can have all these sort of analytic functions completely defined on the strip, which are bounded. And their integral, I guess, is finite. Let's say you take sine squared z over z squared, that integral will be bounded. Although this is not an L1 function, sine z over z. Okay, yeah. So simply because of this condition, this is the technical condition we needed, so that we can assume that LT times FT is an L1 function, uses boundedness of F and L1ness of L. Okay. So all we need to prove is that the integral over these lines, as this capital R goes up to infinity, kind of vanishes. And that is simply because this goes to 0 as R goes to infinity. Because remember, L is Fourier transform of something in F, right? And F consists of CC functions, L1 functions. And Fourier transform of an L1 function by Riemann-Lebesgue lemma, it is a continuous function vanishing at infinity. So in fact, this function L will vanish at infinity. So this will go off to 0. So because of that reason, whatever integral you will have here, it's a bounded strip. So that will go to 0. Okay. So this part is proved, that integral LT FT dt under these conditions, L belongs to inverse Fourier transform of this family F. So this holds. So having said that, so in particular, you have integral R LT alpha TA BU dot U dt will be equal to integral R LT plus I alpha TA U V star U. I'm just replacing my F by the functions I care about. So here's so given any k, in fact the L was in this family F hat, and A in R, and alpha t, whatever that one parameter automorphism group we had, then this mapping. So effectively, we're trying to take a Fourier transform of K. If you notice, we are trying to send this to something in F. So if I look at this family, this is a conjugate bilinear blah, 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 right? Bilinear functional, which is norm-bounded, right? Because K of T is norm-bounded. So because of that, I can define something like AK. So AK associated with this, so that AKXY is equal to this. Or in other words, you can roughly think of AK as being some sort of Fourier transform. AK is the operator R. So KT alpha TA dt. I have integrated out T, right? I will end up with an operator. So now roughly what you will have is, I just did this for this sort of functionals. This typically you'll think of as omega XY acting on alpha TA. Now if I take combinations, linear combinations, maybe countable linear combinations, I will get any WOT continuous linear function, right? So in the end, what I can conclude is that, so I want to use rho. Yeah. Yes. So what do I have? I have rho of AK is equal to integral of K of T, rho of alpha T of A dt. So here what I'm trying to prove is AK in fact belongs to R. So now if rho vanishes on the one Neumann algebra, that means rho of alpha T is 0, right, throughout. So from here we conclude that if rho is WOT continuous and vanishes on R, then rho of AK, don't think of K as an integer, K is a function in F this, is 0, right? So what does that tell us? By Hahn-Banach, it tells us that AK must be 0, or rho must be 0, sorry. Since, so this implies AK belongs to R. Sorry, I don't want to conclude rho is 0 or AK is 0, my bad. What I'm just trying to say is by Hahn-Banach theorem, you can conclude that AK must belong to R. Otherwise, there will be a separating functional, separating WOT continuous functional, which vanishes in R, but does not vanish on AK, right? So yeah, what we have proven is that for any such K, AK is in R. And then another thing that we need is AK acting on my special cyclic vector U. So for that, I'll have to do a very brief computation. Since I'm being very loose anyway, so let me not do the brief computation. So I have this expression right here, right? So AK of U is integral R KT of alpha T A U dt. And what do we know about alpha T A U? By definition, this is UT of U. Now the U has made an appearance, right? So we are going in two divergent string. Now we have kind of met, UT has made an appearance. So K, yeah. So this you can equate to K hat of H A of U. Because UT I'm writing as E to the ITH by Stone's theorem. I have such a possibly unbounded self-adjoint operator such that this holds. And remember, part of the assertion was that if I have an L1 function, then F hat of H is nothing but integral of F of T E to the ITH dt. This was the assertion, right? So that's exactly what I've done. I've written AK of U as K hat of H A U. Okay. So we are nearing completion, but I will leave it. So I said, like, we'll reinterpret the modular condition. So here we have almost arrived at the reinterpretation of this modular condition. So ALBU dot U B star U, where K of Z is defined to be L of Z plus I. So why is that? So what we have is integral R LT of alpha TA BU dot U dt is equal to integral R L of T plus I alpha T of A B star U dt. This is the thing that we first proved, right? Using so LT FT is equal to LT plus I FT plus I. That integrals are the same. So then from here, is it clear? From here, how do I conclude this? So AL, yeah, you just have to look at the definition of AL. What was the definition of AK? AK of X dot Y is equal to this, right? This is how we had defined our AK. We had looked at this conjugate bilinear functional. This is how we defined AK. So from here, you just interpret what in terms of AL. This is AL. This is my vector X. This is my vector Y, right? So this is nothing but AL BU dot U. That is the left-hand side. The right-hand side is nothing but AK. I mean, that's the definition of K. It's just a translate by I. So you have AK acting on U, and you have B star U. So here you're thinking of U as your X and this as your Y. So this is clear. Now this is going to be our interpretation of the reinterpretation of the modular condition. So I'll write it in a little bit more suggestive manner, and I'll leave it at that, and we'll finish this off next time. And we'll start talking about unbounded operators and make all of this rigorous. Okay, so a little bit of manipulations here. So I'm looking at AKU B star of U, which if I think of, so BU, so on the other side, you had ALU, ALBU dot U, so which is nothing but BU AL star U. And this right here is BU S star AKU. right? I think that's what we had. BU. So if I apply J here, and so then what you end up with is, it's a conjugate linear thing. So you'll have a J. I think if you work this out, it turns out to be BU S star AQ. Now from the equality of these, you have the equality of these two things, which means S star AQ is equal to AL star U. Now, if I multiply by S, then I have delta inverse, equals ALU, right? Because S of AL star U is just ALU, right? So all things considered, what do I end up with? Yeah. So delta ALU is equal to AKU. So this is the modular condition, new modular condition or reinterpretation. So remember, what is it doing? So we are always thinking as generator of translations, right? Isn't this a translation? You have this function L and K, and the way we have defined our K, where is that K? Yeah. So KZ, remember, is nothing but translation of this in this imaginary axis. So delta in some sense is, and you could do this for any A, right? We started with the A, and this AL and AK were associated with that particular A, right? So as you are changing your A, this is changing. And so this delta is behaving like a translation, but in a different sort of direction. So using this fact, we will be able to show that UTA UT star is equal to delta to the IT, delta minus IT for all T. And then we'll be done. So I think now is a good place to stop. I think we are all hungry. So are there any questions, quick questions? Okay, if not, we can resume next time. So what we'll do is wrap up this proof, or like proof in quotes, because a lot of unbounded operator theory has not been really talked about. But then what we'll do is start with very basics of unbounded operators. We'll define what an unbounded operator is. We'll define like what are the important concepts and what a self-adjoint operator is and how subtle that idea is. And we'll talk about that. Maybe we'll spend 2 or 3 lectures on that. And then we'll come back and redo everything that we have done, but we'll be much, much faster because now we understand like what are the strategies of the proof. It will just be about filling in the proofs of the lemmas and whatnot in there. Okay, so see you next week.